145 newtons over 1.2 centimeters squared. And there's 100 centimeters per meter. That's squared. And that will be 145 divided by 1.2 times 10 to the 4 Pascal. And I need this to be a megapascal. So 1.21 times 10 to the 6 Pascal. It's very little amounts of megapascals. Well, okay, I'm going to multiply all these by 1,000, or by 10, just so I get numbers that are a little bit more realistic. So that's 12.1 megapascals. And then go ahead and fill that in. The number of significant digits I've got here in these columns is never more than 2. So that's why I'm limiting my stress levels to 2 significant digits. This is still a very weak material. So maybe this is like not metal. The method works. All right, so I've got my stress levels, right? Strain is the change in length over the original length, and this is in the gauge So the gauge length was 0.8 centimeters. So we take each of these numbers and divide by 0.8. Okay. So I'm talking about data collection. I'm just talking about resulting in a load versus extension curve. Characteristic data, that's the elastic and the plastic regions. And now we're doing this converting tensile test data, converting extension or load extension to stress strain. So this is my characteristic data, load extension, I want to convert it to stress versus strain. All right, so let's see, my maximum stress is 51. And my strain to 16. Okay, so now I can just plot 1, 3, and 12 up there. 9, 3 there. Obviously, if you have Excel, you'll get a lot more accuracy. I'm just illustrating how we do this. Okay. 2.5 is at 34. so this curve is linear. Linear, and then like that. Okay, so now I've got my stress versus strain curve. From the stress versus strain curve, I can calculate ultimate tensile strength. Ultimate tensile strength is just the maximum stress. And I picked that maximum load at 6,100, so the maximum stress is 51 megapascals. You see that? And it's useful information to know how high this would go, but it's not useful for design. Because I never ever want to get to that level. The yield strength is a much better measure of design. And so I said yield strength was the stress at the 0.2% offset strain. So how to get that is you go to, on the strain axis, 0.002, because 0.002 is equal to 0.2%. You go to that point, and you draw a line parallel to the original curve. Until it crosses your data. And that stress level is your yield strength. So my yield strength is, I'm going to say about 43. So yield strength means the stress level at which I would get 0.2% strain. So remember when we were first doing this, and I went to a certain level, and then I unloaded? What we're saying is, at what stress level would I be if when I unloaded, I had 2% strain, 0.2% strain? What stress level would it take until when I unloaded, I had a permanent strain of 0.2%. That's where that comes from. It is not a line drawn from 0.002 straight up. That's probably the most common error. And this slope has to be equal to the original slope. All right? So we've got ultimate tensile strength, we got yield strength, and then modulus is the change in stress over the change in strain in the linear or the elastic region only. So I can pick, I see that it's going nonlinear after this data point here. So these first three are in the linear region. So I can choose any two of those three. Do not choose the 0.00. Okay? Between the 0 and the first data point, there's a lot of adjusting that sometimes happens in the setup. And so you can't use the 0.00 as a data point. All right, so I would say 23 minus 12 megapascals divided by 0.0019 minus 0.0013 strain. So I'm getting 1833 megapascals. The modulus is usually given in gigapascals, which is 10 to the 9. So that would be 18.3 gigapascals. Modulus is typically around 1,000, on the order of 1,000 times bigger magnitude than the stress. All right, so try this. So you've got, this is a two-sided deal. You've got load extension data, you've got a table, and you've got a graph. We're going to try and do it in class. I'd like you to do your own, but you can work with someone else. That's okay, but I'd like you to do your own.